The Chancellor is Excellency Dr. Thabo Mbeki, the Vice Chancellor and Principal of the University of South Africa, Professor Puleng Linkabula, to the professor that we are installing this evening, Professor Edward Nxumalo, his family members, friends, loved ones, members of the College of Science, Engineering and Technology, management staff, in particular the Executive Dean who's across the seas and now is watching this lecture, academic and administrative colleagues, UNISA students and visiting students from other higher education institutions, supporters, funders, and UNISA alumni, distinguished guests, boys and girls, and most importantly, a kingpin, Professor Nxumalo, the celebrity of the day, Molweni, Sanbonan, Tobelang, Dumelang, Sheng, Goeienaand, Jambo. I acknowledge all protocol. My name is Professor Tenjiwe Meiwa. I'm a vice principal that's responsible for research, postgraduate studies, innovation, and commercialization at this university. Ladies and gentlemen, colleagues, I welcome you warmly to Professor Nxumalo's inaugural lecture. Professor Nxumalo is a professor, a full professor that is at the College of Science, Engineering and Technologies Institute, a research institute we refer to as the Institute of Nanotechnology, Water and Water Sustainability at the Science Campus. This has been his status since January this year, 2021 last year, I mean. Please allow me to acknowledge the Acting Executive Dean, Professor Dube, who is participating actively in this evening's program. We also welcome Professor Nxumalo, who is a professor at the School of Chemical and Energy Engineering in Malaysia. Professor Nxumalo serves as a respondent during this installation, and we thank you, Prof, for heeding our call. We live in turbulent times, in times wherein the relevance and role of whatever we do in our research, in what we propagate, has got to make a difference in what we do. Hence the importance of this lecture by Prof. Nxumalo this evening, a professor in one of our institutes that we hold so dear, the Institute of Nanotechnology and Water Sustainability, the content of which you will be bedazzled with. It's a lecture that speaks directly to our heart in terms of what we should be doing to bring about change in our societal ills. As an institution at UNISA, we are bound to produce these kinds of work, these kinds of professors, whom you shall be knowing more about, of the kind of Professor Edward Nxumalo, as the Acting Executive Dean, Professor Dube, comes to the podium to tell us more about his resume. It is a proud moment for us to grow a professorate this substantially and add the expertise that we see in Professor Edward. Hence, we refer to him as a full professor that we install and inaugurate this evening formally. Professor Nxumalo is a full professor because of the awards that he's received, the honors that he's been able to have, his leadership in leading research projects, his mentoring stances, if I may say so. In essence, he's a producer as well as reproduces himself through his students, his mentees, through the research work that he does, through the research funding that he gets. This we hold him very dear because of the work that he does to put the university at the level at which it is right now. It is to this end that I request that through the chat box you congratulate him, make comments, words of you've done well, whatever, but also in doing so, take cognizant when he comes to the podium in terms of what he will be delivering to us. And when you do that, please be sure that you also give him some ideas from your experiential life as how you experience his working field. For him, it is scholarship, it is science. For you, as the patrons of this lecture, of course, it is what you live on a daily basis. So let's use this lecture to bring about change and make a contribution to his scholarship, because with him being a full professor, his research work and his contribution to societal change that we seek to see does not end. Therefore, ladies and gentlemen, at this juncture, I want to call upon Professor Dube, the acting Executive Dean of the College of Science, Engineering and Technology, to come to the podium to introduce Professor Nxumalo. After her, we will have Prof. W.J. Lau, who's our respondent, to respond to the lecture. Professor Lau, you'll know more about him later, but it is at this time that I invite Prof. Dube to come over to the podium. See you a little later. Thank you.
Good afternoon to all of you. I would like to acknowledge Professor Lingabula, the Principal and Vice Chancellor of the University of South Africa, Professor Tenjue Meyiwa, who is the Vice Principal, Research, Postgraduate Studies, Innovation and Commercialization. I would also like to acknowledge the respondent for the speaker tonight, who is Professor W.J. Lau. He is the head of Advanced Membrane Technology Research Center at the University of Technology in Malaysia. It is my pleasure, colleagues, to read to you and introduce Professor Edward Nxumalo, who is giving his talk, his inaugural talk for tonight. Professor Nxumalo is a professor at the Institute of Nanotechnology, Water Sustainability in the College of Science, Engineering and Technology at UNISA. After receiving his doctoral degree at the University of Witwatersrand in 2010, Professor Nxumalo went on to conduct his postdoctoral research at the University of Johannesburg in the Department of Applied Chemistry, where he was later appointed a senior lecturer. During this time, he was involved in lecturing undergraduate chemistry courses in the faculties of Science and Engineering, while pursuing his research on the production of diverse nanomaterials, including carbon nanomaterials and their application in membrane systems. In 2015, he joined the then Nanotechnology and Water Sustainability Research Unit at the University of South Africa as an associate professor, where he was involved in the supervision of master's and doctoral students. During this time, he also mentored emerging researchers and staff members and was a leader for strategic research groups in nanotechnology and membrane science technology. During his tenure as an associate professor in the university, Professor Nxumalo received multiple research grant awards as a principal investigator. These include the National Research Foundation, that's NRIF, South African Oman Bilateral Grant, NRF Tutuka Grant, UNISA's Innovation Support Program Grant, as well as the Water Research Commission Grant, thus making a significant contribution to the third income stream generation of the Institute. In the year 2021, Professor Nxumalo was appointed as a full professor in the University of South Africa, and in the same year obtained his CR2 NRF rating, a remarkable achievement. Consequently, he managed to attract the Sasol NRF University Collaborative Research Grant to the tune of 4 million for the period of 2022 to 2025. The funding was awarded towards his pioneering research project on the photocatalytic carbon nanotube-based nanofillers and their subsequent use in the development of solar-driven membrane system. Recently, he was awarded the Technology Innovation Seed Fund to pursue his innovative project towards the production of a light-enabled self-cleaning water filter. To date, Professor Nxumalo, a passionate scholar, has authored and co-authored over 100 peer-reviewed scientific research papers in accredited journals, book chapters, and conference proceedings. He currently sits on boards of various national and international bodies. He is also a member of various scientific and editorial committees. He is a notable and prominent speaker in national, international, governmental, scientific, and public meetings where he talks about the merits of nanotechnology, membrane technology, and water treatment systems, as well as their benefits to the general society. Professor Nxumalo is a leader of the Engage Scholarship Project for the Institute, which serves to provide nanotechnology solutions to rural communities based in different provinces in South Africa. He further assists in supporting the strategic direction, academic and operational activities of the Institute through Engaged Scholarship Project. In addition, Professor Nxumalo is the incumbent president of the South African Nanotechnology Initiative, a technology association mandated under the Department of Science and Technology. As a leader of this organization, he is the host of the International Conference on Nanoscience and Nanotechnology in Africa, widely known as Nano Africa. He is also a steering committee member of the South African Research Infrastructure Roadmap, which provides strategic guidance to the Department of Science and Innovation on infrastructural planning for science, engineering, technology, and innovation system. He was the chair of the Second African Membrane Society International Congress in 2018, where international scholars in the field were hosted, and currently serves as the vice president for this network after having served as its director for international affairs for many years. Professor Nxumalo has been able to achieve all the career milestones mentioned above through the unending support of his family, friends, students, mentors, collaborators, funders, and partners. We therefore acknowledge their presence in the inaugural lecture today. We further do recognize the presence of a number of national and international guests from academia, industry, government entities who are attending his lecture today. Ladies and gentlemen, I would like to invite Professor Nxumalo to present his inaugural lecture.
Thank you, Professor Dube, Acting Executive Dean in the College of Science, Engineering and Technology. I wish to thank our Principal and Vice Chancellor in the University of South Africa, Professor Puleng Lenkambule, Professor Meyiwa, Vice Principal for Research, Postgraduate Studies, Innovation and Commercialization, Professor Peggy Mamba, Executive Dean for the College of Science, Engineering and Technology. I also wish to thank my respondent for the day, Professor W.J. Lau from the University of Technology in Malaysia. Thank you indeed, Professor Dube, for such a wonderful introduction. For a moment while you were reading my citation, I thought somebody else, not me, was being introduced. Thank you for this wonderful opportunity to share a reflection on my academic journey and to share the body of knowledge that I've been involved in the past 10 years or so. It is incredibly humbling to share this space with so many prolific scholars whose work continue to shape the academic landscape in this country and beyond. It is a matter of personal pride to be standing in this podium today. I therefore wish to recognize the honor and trust given to me by this great university, the University of the Land, as a full professor. I would like to share my research journey with you, and today I decided to talk on breakthroughs in carbon-based nanostructured membranes, desalination, and beyond. This work is born out of my undying love for materials or material science, or nanomaterials if you like. I like playing with diverse advanced materials that have different structures and functionalities, studying their unique and intriguing properties at dimensional scales and applying them in real-life situations. I would like to start by introducing you to my outline for the day. I will start with introduction and terminology, membrane technologies, our contribution so far, perspectives, and outlook. I will then finalize my lecture by giving my final remarks. Let us give some highlights and describe some important terms. Our topic can be broken down to nanostructured carbons, membranes, desalination, and if you like, beyond. So, what is a membrane? A membrane is a selective barrier that allows some things to pass through but stops others. Such things may be molecules, ions, viruses, and other such small particles. Let us first take a look at a COVID mask. What is the purpose of a mask? We all know that it is to reduce transmission, to prevent pre-symptomatic spread of the virus, to protect yourself from getting sick. It is also a good hygiene practice in general to put on a mask. Well, a mask is in fact a membrane when you think about it, or is made out of a membrane, because it is a selective layer that regulates the passage of things in and out of your mouth and your nose. So a mask is a membrane. Let us move to the next term, nanostructured carbons, or carbon nanostructures. For those of you who jumped out of the physical sciences class early in your life, I sympathize with you today. But for those of you who didn't, you will recall that carbon is considered as an unusual element situated at position 6 of the periodic table due to its bonding configuration, which is unique, and the way it interacts with other elements. Nanotechnology is the understanding and control of matter at a nanoscale, which is the scale between 1 nanometer and 100 nanometer. So, nanostructured carbons or carbon nanostructures can be referred to as carbon materials whose structural elements or properties have dimensions in the range of 1 to 100 nanometer or in the nanoscale. Let us look at the morphology of the word desalination. Desalination has two structural elements, D, which means remove, and saline, which means salty. It is also normally referred to as desalting or desalinization. So desalination can be defined as a process of removing dissolved salt from a salty water body, such as seawater, in a process referred to as seawater desalination. By the way, desalination can also be applied in brackish water, highly mineralized groundwater, and even municipal wastewaters. In South Africa, in the past months or past years, we have lived under the fear of what is called day zero. Many pictures, such as the one shown on screen, were circulating in media spaces. These included pictures such as dry water sources that you see on screen, people moving around with containers to collect water from tanks, and people cutting down trees, claiming the trees are competing with them for water. Desalination plants were manufactured in the regions to curb this problem. Scaling up our efforts in this country and in Africa in general will help to significantly alleviate or eradicate the problem of water scarcity. So, ladies and gentlemen, today these are your key terms which capture the theme for the day. We have explained some of them, but not all of them, but they are all interrelated. Later, we'll delve much into the details, such as examples where necessary. Let us now move on and talk about fundamental elements of membrane separation processes. Later, we will touch on nanostructured membranes and membranes that uses carbons. First, membrane classification can be divided into materials, membrane configurations, operational conditions, and the example of each are shown here. The focus for today will be on materials, where we will actually look at membrane materials that are used in membrane systems today. Another method of classification includes material. As will be shown later, membrane may be organic or inorganic, and the structure may be porous or non-porous. Membrane can be classified according to pore size range as shown on the table, and hence applications as either microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. Of course, I did not explain all other types of membranes. As already explained, particles of different sizes, types, properties are separated by each membrane type. Of course, such processes depend on the mechanism of sieving and various other factors. The focus for today is on nanofiltration and reverse osmosis when we deal with desalination. So, desalination technologies can have a wide range of methods. One of them is thermal desalination process, where water is heated, evaporated, condensed, and collected. Such processes produces clean water and brine. Some examples include multi-stage flash desalination and membrane desalination and membrane distillation. So membrane distillation, for example, include the use of hydrophobic type of membranes, depends on the volatility of the separating component, and also depend on the structure of the porous membrane. The second one is the membrane desalination process. As I've already said, the most common example of desalination process is the reverse osmosis. And I think at this stage, all of you are specialists now in RO. RO seawater desalination has many advantages, such as the one shown on screen, including saving energy, lowering capital cost, short startup and shutdown times, and many others. We now move on to talk about new innovations in membrane technology. Such innovations have led to a new generation of advanced membranes made from the process of nanotechnology. Conventional membranes briefly include inorganic membranes such as mesoporous ceramic membranes, or organic membranes which may use different types of polymers, including polyethersulfone, polyvinyl difluoride, polysulfone, cellulose acetate, and many others. Amongst all types of examples that are given today on nanotechnology-based membrane materials, we will focus today on mixed matrix membranes and vertically aligned nanotube membranes. As an example, there are different types of nanoparticles that have been used in membranes. This is because nanotechnology enhanced membranes of diverse types, employing various nanoparticles as shown on screen, are possible to be made and have great potential to be implemented in desalination, and hybrid membrane processes due to their well-defined nanostructures and nearly limitless surface chemistries. Properties of such include reduced fouling rate, antimicrobial properties, enhanced hydrophilicity, rejection of salts, and many others. As already mentioned, carbon is one of the most widely exploited elements that has been used in nanotechnology. This is because of its many fascinating characteristics, including the important ability to bond with itself. And in so doing, this has led to carbon being able to form different types of dimensions, including 0-dimension to 3-dimension carbons. Here are some examples. So graphene, as I've already mentioned, is viewed as the foundation of the structures of many carbon allotropes. So graphene is a carbon allotrope in the form of a sheet consisting of sp2 type carbon arranged in 2 dimensions. For an example, graphene can be wrapped up to form a 0-dimension fullerene on B. It can also be rolled to form a 1-dimension single-walled carbon nanotube is an example on C. Graphite contains multiplanar layers of graphene stacked on top of each other to form 3D structures in D. These are some of the examples that are known of 0-dimensional carbon allotropes, including fullerene, spherically shaped carbons, and carbon dots of different types. These are examples of 1D carbon allotropes, including carbon nanotubes and carbon nanofibers. Examples of 2D carbon allotropes include graphene, oxidized graphene, and graphene quantum dot, which have diverse properties. And finally, 3D carbon allotropes include graphite and porous carbon frameworks, which have got intriguing properties that could be used in membrane fabrication processes. All these materials possess key properties enabling them to be used in membrane fabrication processes, such as nanofillers, support, or agents of change in tuning properties of membranes. One of the widely known properties that carbon nanotubes or carbon nanomaterials can have is the ease of functionalization that change the structure, as we will see in the next few slides. Modification, as I've already mentioned, of such carbon species significantly transform the chemical and physical properties listed in this slide. The structure and interface modification of carbon nanomaterials have been considered as valid methods to enhance their properties. For example, in A, we illustrate how pore sizes of carbon nanomaterials can be altered in such a way that targeted pollutants are adsorbed on the surface. And in B, we illustrate how can one attach a carbon terminal site. This therefore further enables the attachment of functional groups that can interact with specific pollutants. Surface modification, such as regulation of the diameter or lateral size, pore size, or surface area, can be achieved by using size control or texture templates such as silica sol, shown on your left, or sol gel, shown on your right, to make, for an example, mesoporous carbons. These are widely used techniques and help to control the porosity and other functions. The differently hybridized carbon terminals enable modulation of carbon nanomaterial surface chemistry by incorporating surface group. These include acid treatment, nitrogen doping, or sulfur, nitrogen, and boron doping, or a combination of this. It is shown that carbon dots can be used as carbon substrate for the synthesis of different dimensional carbons, such as one-dimensional assemblies, two-dimensional assemblies, and three-dimensional assemblies. The products are usually porous and they contain high surface areas and are functionalized without the need for further modification. So, modified nanocarbons through doping and functionalization or wrapping or even other means are used as fillers in the casting solution. They influence properties such as surface pore size, hydrophilicity, sublayer porosity, surface roughness, and surface charge. These lead to a wide range of membrane structures, such as nodular structures, finger-like pores, microvoids, porous network, as will be shown later, and many others. The slide here presents some other common functionalization trends that are seen today and other possibilities shown on the picture on your right. Hydrogen bonding of functionalized CNT polymer matrix and its effect on membrane solution viscosity is shown in this work. It is shown that variation of the viscosities of CNT addition can be seen to control the ultimate morphology, and this will be discussed in the next few slides. Functionalization of CNT membranes with positive, negative, and hydrophilic groups is also possible via what is called tip functionalization and core functionalization. I would like to now move on to discuss vertically aligned CNT membranes that are common nowadays. Methods for vertically aligned CNT membranes include polymer infiltration, liquid-induced deacidification, self-assembly and filtration, as well as the common phase inversion process. Such methods are normally differentiated by the type, their manufacturing methodology, their support used, configuration, and their performance. So here are possible scenarios from the methods that I've just explained. One, you may have vertically aligned CNT assembly. You may have mixed matrix CNT membranes. And on the lower picture, you may have the CNT themselves coated on the membrane surface or support. And finally, the CNT can be coated on the membrane support as an intermediate layer. Some of the properties of such CNT membranes include high rejections to the value of 100% rejection. But of course, this depends on the sizes of the diameter of the membranes. There are other properties which are improved, especially pore density and the flow rate, and pores per square meter or per centimeter square. As I've already mentioned, some of the factors that affect the flow of water molecules in the tube channels in CNT-based membranes include modifications, the length of the, for example, CNT, the external conditions, and what is called the italicized angle, shape, and the diameter. In this table, we present the diversities in vertically aligned CNTs and versus the CNT mixed matrix membranes. It is shown in this table that the vertically aligned CNT types have complex fabrication processes and can be very expensive when applied in these processes, while the CNT types use conventional processes and are readily commercializable. This screen demonstrates the role of bridging agents. It is one of the common route nowadays where you have a bridging agent in yellow color forming a bridge between the nanofiller in gray color and the polymer matrix represented by the brown color. I now present the manufacturing types of VA and CNT membranes, or the manufactured types of vertically aligned CNT membranes on the left, on the top screen, as well as the lower one on thin film membranes and the bottom, which can be nanofiltration membranes. These are the mainly used types for desalination membranes. Of course, on the right, I present one of the methods that is used for fabrication. There are diverse possible pathways for water transportation in CNT-based membrane or in CNT polymer blend membranes. These are due to, one, the hydrophobic effect and enhanced transport, which happens between the CNT and the polymer. Two, the nano-confinement and hence flux, which happens in between CNT adjacent to each other. Three, ultra-fast transport through the CNT pores. And four, direct transport through the membrane matrix. These normally result to membranes with high flux and high rejection of unwanted species. The work by Zhang et al. Shown on screen demonstrate the effect of oxidized CNT and graphene oxide on the fouling control of BSA and anti-fouling mechanism of the membrane made from PVDF. There's a strong interaction between the fouling layer and the PVDF membrane, while there is a weaker intermolecular adhesion force between the CNT and GO and the BSA foulant. In this case, nanocarbons are used as fouling control or as anti-fouling agents. Another common method is the bulky paper membrane fabrication method, as shown on screen. We do have a variation on the type of membrane that can be made from CNT membranes. This could be flat sheet CNT mixed matrix membrane or hollow fiber mixed matrix membranes, which may have different properties. The difference on these result on their use in the membrane fabrication processes, especially during filtration. These are some of the examples. On the left, flat sheet from our recent work, and on the right, hollow fiber membranes. Before I move on to our contributions so far, I would like to just summarize what we've learned in the last few slides. We've learned that we have first made a broad overview of the production techniques in CNT membranes. We've also learned that there are diverse types of carbon-based membranes, including CNT bulky papers, isoporous carbon nanotube membranes, in which the nanotube act as channels, as well as the CNT mixed matrix membranes, we've also learned the studies, we've also summarized studies on the effect of CNT addition on the membrane properties. We've looked at the possibilities of flat sheet versus hollow fiber membranes and their potential application on CNT membranes, especially in desalination and other water-related applications. I now move on to our contribution so far. I will just make some key highlights from our work. This is one of our work that we have carried out on microvoid-free membranes, which has improved mechanical strength, anti-fouling, and antibacterial properties. The idea here is to produce a membrane with good performance properties while maintaining a good mechanical strength. These membranes are born from method referred to as non-solvent induced separation, phase separation process, which normally uses water as a non-solvent and carbon nanotube as nanofillers. The parameters are shown on screen. Such membranes have a high stability due to the stability of the solution, even after 4 weeks. This is due to the unique interaction where no separation occurs between the CNT nanoadditives and the solution. We have shown that CNT disrupts the internal structure of the membrane completely, as shown on the same images. The low tensile strength, which is shown on the table, is achieved due to the weakened membrane, which is a result of pressure points in the structure caused by CNT inclusion. Upon the addition of PEG 20 kilodalton as an additive, the formation of a sponge-like microvoid morphology is achieved as shown on these same images. It was postulated that PEG form bridges between the nanoadditives and the water. The PEG improves pore interconnectivity, thus preventing the formation of microvoids, whereas water increases casting solution viscosity and bring the doped solution viscosity closer to what is referred to as the binodal composition, where the suppression of the microvoids is favored. Here, we further show that the internal structure is not just a dense structure, but it is the needed open porous network. The casting solution viscosity increases with an increase in temperature due to the increase in the mobility of the polymer chains. The casting solution viscosity increase with the increase in the addition of the CNT concentration due to the strong hydrogen bonds that are formed between the sulfonyl, water, and the carbonyl group, as shown on the screen. It was found that the tensile strength is significantly enhanced. And this tensile strength is comparable to that for those membranes supported on a non-woven fabric. The pure water fluxes were measured, and it is shown that they increase with the inclusion of CNT and then reduce further with the increment. This is a result of the combined effect of the enhanced hydrophilicity and the agglomeration of CNTs at higher loading. The FFR values, which are shown on the right-hand side of the screen, were found to be higher than those for bare membranes. And even after the second fouling and the cleaning stage of M5, it was found out M5, which is the membrane with the highest concentration, has the highest FRR value. In terms of bacterial studies, we have found that the bacterial killing ratio was at 85%, whereas it was at 99% when M5, the membrane with the highest CNT loading, was used. CNT membranes were then made for brackish water or brackish groundwater desalination. The structure made for this application is a thin film nanocomposite membrane, as shown on the right-hand side. The process includes soaking the support layer in MPD, immersion in TMC, and rinsing with water to form a thin film composite membrane, which is later put in a solution of silver nitrate and further reduced to form the final nanofiltration membrane. The nanofiltration membrane was made on a support prepared via the NIPS method, as presented earlier. It has a higher mechanical strength. The surface morphology changed from a relatively smooth surface to a granular surface. Upon the introduction of lower content of the monomer DABSA, the membrane surface morphology, as shown on the screen, changed from a polyamide granule to consist of cross-link structures with ridges and valleys. This is due to the increase in the cross-linking degree of the polymer layer upon addition of the aromatic diamine monomer. Comparison was made based on pure water permeability, salt selectivity, and operational pressure. Membranes displayed high water permeability and high monovalent or bivalent salt selectivity at low operational pressures and salt concentration in the range of brackish water salinity. Further, static adsorption experiments for E1, a well-known hormone, have also been carried out. Studies carried out include pure water flux and in different pressures, zeta potential against pH, and adsorption as a function of time and membrane area. The properties were measured in terms of size, membrane thickness, and molecular weight cutoff, as shown on the table. We then moved on to work on carbon nanotube titania as nanofillers. The picture shown on screen present different possible configuration of CNT titania composite from our earlier studies. Different types using amorphous carbon nanotubes and amorphous nitrogen-doped carbon nanotubes were achieved. Also, we measured the different sizes of the nanohybrids in preparing them for use in membrane fabrication processes. TiO2, for an example, and NTiO2 demonstrated good properties that they could be applied in such processes. High adsorptive removal of a dye, referred to as reactive red 120 at pH 2, was attributed to the positive hydroxonium ion being electrostatically attached to the dye, and therefore imputing a positive charge, whereas the nanohybrid have a predominant negative charge. So we then moved on to carry on the polyethersulfone-based membranes through surface group enriched TiO2 CNT nanohybrids. It is shown that the microvoids were due to the migration of the nanohybrid to the surface during demixing. This is well presented on the same images on screen. Also, the surface pore size decreased with an increase in the nanoparticle loading. In terms of the permeability and the contact angle, it was found that there is an increase. It was found out they do increase with an increase in the photocatalytic filler loading into the membrane. Further, dye rejection was found to be higher for the nanohybrid loaded with the highest amount of the titanium. Absorption of the reactive RR120 dye onto the membrane was found to be higher at low loadings, and also increases with an increase in the pore radius. On this work, the membrane demonstrated that they are able to remove color under UV irradiation. The UV visible spectra therefore demonstrated both decolorization of the dye and mineralization of the dye. The photocatalytic membrane under sunlight irradiation therefore demonstrated self-cleaning ability as shown on screen on the membrane with the highest nanofillers. Lloyd's work has produced and characterized unique adsorptive graphene oxide-based PVDF membranes that have cyclodextrin additives using a normal phase inversion process. The excellent adsorption properties are attributed to hydrogen bonding interaction, inclusion complexation, electrostatic interactions, and pi-pi interactions as shown on the mechanistic model presented on the right-hand side. Further, CNTs have been found to enhance key properties for membrane distillation, namely hydrophobic, superhydrophobic, hydrophilic, and omniphobic properties. These materials are normally fabricated using the electrospinning technique. The electrospinning machine consists of a high voltage supply connected to a collector and a syringe tip. As shown on screen, the polymer solution in the syringe is pulled by electrostatic forces towards a collector during this process. The solution creates create a tailor cone shape and form nanofibers as it stretches and collected on the collector screen.
Excuse me, Prof. Just 1 second before you continue.
Thank you.
Okay, you can continue, Prof.
We have also made super hydrophobic and super oleophilic PVDF membranes for oil-water separation. The work for MOHO shows the process involved, which include oxidation of the CNTs, wrapping, and electrospinning to form a nanosponge, which is used in oil-water separation. Some properties of the PANI or polyacrylonitrile as one of the most used polymers for electrospinning nanofibers is shown on screen. And they start from the wide pH tolerance down to their dissolution in most organic solvents. This work therefore illustrates the optimization of the core polymers used during this process. The addition of, for example, cyclodextrins affect the morphology of the PANI nanofibers at optimized electrospinning conditions. These nanofiber membranes were then used for the simultaneous degradation of dyes and micropollutants. We have also achieved nanocellulose-based nanofiber membranes that incorporate carbon nanomaterials. We start with nanocellulose extraction from, for example, plant materials, followed by electrospinning and casting of the nanomembranes. We also study their thermodynamic compatibility. Methylene blue dye and heavy metal absorption was achieved through various process mechanisms that are shown on the picture on the right-hand side. We have also demonstrated the use of CNTs to treat beauty hair salon or municipal wastewater. And we show on screen chemically cleaned membrane and its corresponding EDX mapping images after treatment. We have recently made fluorescent n-doped carbon doped on the work by Temba and Olet, which are supported on solid carbon spheres or solid silica spheres. This work has not yet been incorporated into membranes, as we are still studying their properties. This slide demonstrates 10 micrographs of nitrogen-doped graphene oxide and graphene oxide quantum dot that we have applied recently in membranes. And here we show that PS electrospun nanofiber membranes can indeed be embedded with graphene oxide and quantum dot with different sizes. And recently, we have started opting for the use of other hydrophobic materials such as boron nitride nanosheets and effectively apply them in oil-water separation. These are other types of work that we are carrying out which are not included in this presentation. As I am nearing end to my talk, I would like to touch on some consideration. There are so many hurdles that this work is facing and they need to be addressed. One is cost effectiveness, scalability, stability, unclear mechanisms, suitability in current desalination systems, environmental sustainability, and reproducibility. As I am about to make my final remarks, I have tried my best to break down the topic of the day to you in a very simple terms, although at times I fail to resist the temptation of using scientific jargon. I wanted you to have a clear understanding of this subject, especially on how desalination can solve our water-related problems and how nanotechnology can also play a role. I also wanted my 5-year-old son, Persihle, who is, by the way, turning 6 this month, to come out with something from this inaugural lecture today. I also wanted my 9-year-old daughter, Dumo, who has a very inquisitive mind, not to bash me with tough questions during our family dinner tonight. My final remarks also just include the fact that innovations in the application of nanotechnology in membrane systems has demonstrated unquestionable trailblazing potential for use in desalination processes, and that nanocarbons, 0 to D, can actually enhance new physicochemical properties to membranes and should be pursued further. If you forget anything I said today, please just remember that nanotechnologies can be applied in the future to enhance membranes for desalination or to remove salt from water. Desalination is indeed the future for our continent. I do have other personal lessons I've learned from other areas. This is one of the books referred to as The Engines of Creation, which is an exciting book about the possibility of a fantastic future, which was first published 20 years ago. The focus is on the future of new technologies using new machines, including nanotechnology. And the second one is a movie, which is a comedy or drama movie, showing 2 scenarios of someone's life. It shows how a small change in your life or meeting one person can dramatically change your life for a different cause. As I do my appreciation and acknowledgement, it is impossible for me to mention everyone or every organization that has been part of my journey. I highlight names of friends, colleagues, students, mentors, collaborators, co-authors, and others. All this would have been impossible without you. I thank all these organizations and funders for funding and supporting my research in all these years. But now I wish to make a special mention of my wife, Bongiwe, who has been part of my journey, who has been part of all my journey. I thank her. I do have a lovely family, and I'm forever grateful to God. On the left is a picture of myself and Bongi, and on the right is Dumo and Persihle. They make my world complete. I wish to thank you all for listening to my lecture today in the different platforms. I now wish to once again thank the University of South Africa, the University of the Land, for the honor and trust given to me. I am being challenged further to continue shaping African futures in the service of humanity through my scholarship. Thank you.
I wish to greet the Principal and Vice Chancellor of the University of South Africa, UNISA, Professor Puleng Lengabu, Professor Thenjiwe Miyiwa, Vice Principal for Research, Postgraduate Study, Innovation and Commercialization, Professor Simi Dub, Acting Executive Dean in the College of Science, Engineering and Technology. Professor Peggy Mamba, the Executive Dean for the College of Science, Engineering and Technology. I also wish to recognize our newly crowned professor, Professor Edward Nxumalo, who has given an exceptional and thought-provoking lecture today. Professor Nxumalo spoke on his groundbreaking and innovative research on breakthroughs in carbon-based nanostructures, membrane, distillation, and beyond. This is a topic of great interest in the academic space. His lecture today has everything in it. It covers the critical themes in the field, including a view in the world of nanotechnology crafted membranes, fundamental elements of membrane separation processes, a new generation of advanced membrane material from the process of nanotechnology, and dimensional carbons for advanced nanostructures membrane applications. Focus will also placed on the aligned nanotubes membranes and next generation nanofiltration and reverse osmosis membranes, which can be potentially used in seawater distillation. He also gives some important highlight on other types of nanomembranes used in other areas, such as ultrafiltration process, low pressure exhaustive applications, photocatalysis, and many others. The unit of nanotechnologies in seawater distillation is a sustainable technique to supply fresh water in a more efficient and eco-friendly manner for the future. Distillation can offer an important alternative for South Africa, the Africa continent, and other water-scarce regions in the world. As already demonstrated by Professor Nxumalo, innovation in the application of nanotechnology in membrane system will also new dimensions in distillation processes and other relevant processes. Nanocarbons will continue to play an important role in augmenting new physiochemical properties to the membranes of the future and should be pursued until they are fully commercialized. In conclusion, the lecture by Professor Nxumalo was indeed exciting, topical, and useful to scholars in the whole wide world of membranes and is of archival qualities. I suggest that the lecture should be published and kept in archive for reference by future scholars. Professor Nxumalo's scholarships and professorships has been fully demonstrated in many other areas such as academic leadership, teaching and learning, research and innovations, community engagement, and service to the African communities. I thank all those who have supported him. I also thank his family and in particular his wife, Peggy, for her relentless support. I now wish to congratulate you, Professor Nxumalo. You have now reached the pinnacle of your career. I do not doubt that you will continue to make a mark in the world. Once again, congratulations.
That lecture was a real bomb, wasn't it? So was its analysis. As we close and reflect on all the work that we've done this evening, I want to again invite you to further congratulate Prof. Nxumalo, as well as make suggestions about what else could he do in his work going forward. Thanks, Professor Edward Nxumalo, for an educational lecture of this kind, which is an acknowledgement of the extent of your scholarship and its significance in our society and various communities as we tackle matters of water. Through this lecture and its analysis and its importance, we indeed do stamp the fact that we are a university that shapes futures of communities. I appreciate Prof. Nxumalo for the response given and its apt analysis, as I express also to you, ladies and gentlemen, for gracing this lecture as patrons. And lastly, but not least, I want to gaze my eyes on, as I express gratitude to colleagues who never come to the podium but do a lot of work behind the scenes to ensure that these lectures are successful. And I single out the video colleagues, photography colleagues, the IT colleagues, colleagues within the facilities, and colleagues in a corporate media communication space, the Department of Institutional Advancement, for ensuring that these lectures become what we expect of them at the level of excellence that we require and demand. And indeed, this afternoon, from afternoon to this evening as we end, we have experienced all the expertise that comes from the University of South Africa, the University of the Land. You have a good evening. Asante. Ngiyabonga.